Hello, everyone. I'm Whitney Espich, CEO of the MIT Alumni Association, and welcome to the November MIT Alumni Forum. Lately, space has felt a little closer to home. NASA's DART mission confirmed that we can alter an asteroid's path. The James Webb Space Telescope continues to capture worlds orbiting distant stars. And in the past year, scientists have drawn global attention to asteroid 2024 YR4, a reminder that planetary defense is no longer science fiction, but science in action. The same telescopes revealing distant planets are also helping us understand risks here on Earth. Today's conversations brings those two themes together, exploring other worlds while protecting our own. To help us explore this further, our featured speaker is MIT alumnus Julien DeWitt, PhD 14, Associate Professor of Planetary Sciences in MIT's Department of Earth, Atmospheric, and Planetary Sciences, or EAPS. Professor DeWitt's work brings data science and discovery together and helps us better understand worlds beyond our own. He was part of the team that discovered the TRAPPIST-1 system, a nearby collection of 7 Earth-sized planets. This achievement has reshaped how we search for life elsewhere in the universe. And today, his research uses telescopes like Hubble and the James Webb Space Telescope to study those distant atmospheres while also revealing details about small asteroids in our own solar system. Guiding today's conversation is Artem Bordenov, a research scientist in EAPS. He works alongside Professor DeWitt to discover and study new planets and solar system objects using advanced telescopes and imaging techniques that expand what we can see and imagine beyond Earth. If you already have questions for today's discussion, please add them to the chat box below and upvote the ones you find most interesting. Closed captioning is also available, which you can access by selecting the CC icon in the lower right corner of the video player. And now, over to our featured speaker, Professor DeWitt. Welcome.
Great. So thank you, Whitney, and thank you to the Alumni Association for having me today. I'm really, really thrilled, in fact, excited to talk to you about these two topics that are really close to my heart and the research we do here in EAPS with Artem and many others. On the one hand, the search for life, and on the other hand, planetary defense, which means defending Earth from possible impactor asteroids. What I would like you to take away by the end of this talk is the following few messages. First, that exoplanets are key for us to gain new vantage points on key concepts, going from planet formation, evolution, all the way out to atmosphere, climate, and life. They really bring new perspective on top of what we have been able to learn from our own solar system. In addition to that, as we move towards new technology, we gain access to new unparalleled windows into space, boosting a wide range of fields, amongst other, astrobiology and planetary defense. That's what I'm going to be focusing on today. And finally, you'll see through this talk that exohabitats as well as space-based resources are coming on the horizon. And to me, this is a sign that humanity is ready for its next big step on its space odyssey, which is, I believe, really becoming a multiplanetary species. So we'll get to all of that. In summary, what I'm trying to say here is that space has been calling, is calling, and for the first time, it seems like humanity is about or is ready to respond and is ready to make it stand. And obviously, humanity making it stand echoes the famous Carl Sagan speech about our pale blue dot, because like it or not, at this time in our history, Earth, really air, is where we need to make our stand. So, in order to cover all of that, I split today's talk into 3 parts. First, we're going to be looking at exoplanets and talking about what appears to be our next step in our space odyssey, stumbling upon life elsewhere. As it's an odyssey, I'm going to introduce you to the sirens, these exoplanets attracting us to new horizon. There'll be a hero, the James Webb Space Telescope, or JWST, and there'll be the monsters, the chimeras we have to take care of, which relates to our current model that are failing us when it's time to truly interpret the data we're looking at. And as it's a story, there'll be a plot line, and you realize that the plot line we were dealing with before has limitation to such an extent that truly assessing habitability or inhabitability with current technology was not within reach, but we just brought in a plot twist that makes this possible with current technology, so within the decade. So We'll get through all of this. We'll do a break, do a Q&A, and then we'll move to part 2, where we're going to talk about our close neighbors, asteroids that are decameter, so 10 meters or so in size. I'll show you how, by doing the science we do for exoplanets, we've been able to change the game for asteroid science. And quickly after that, use the James Webb Space Telescope to do planetary defense in real time. And then, because it's an MIT audience, I'm going to talk to you about other opportunities, even beyond the search for life and planetary defense. And that's just for alumni. So you'll see how MIT has new prospects just ahead of it that can also help the whole entire world. So stay tuned, that's going to be at the end. All right, so now that this is said, you have the scope for tonight. I can dive into part 1. Part 1 started, more than 7 years ago, but we're going to start this journey 7 years ago, where I was lucky to be part of the team that found the first terrestrial planet around which we can search for signs of life. These are 7 planets found around TRAPPIST-1, and they're important because they have this winning combination of being Earth-sized, temperate, so potentially habitable, and they are around the right kind of star such that we can study them with current technology. What happened next when we introduced the discovery was amazing. We were on daily, weekly, monthly magazine, front page of most top news outlets across the world. And the result was that about a third of the world population appears to have been connecting with our discovery. Now, we didn't find life elsewhere. We only provided humanity with a tangible way to get to assessing the presence of life on the world beyond our own solar system. So the impact it had on the population was, to some extent, quite surprising. But is it really surprising? Maybe not. Because we humans have a very special relationship to space. Space drives technological development, nurtures our imagination. I mean, we've looked at it to time plantation, cross oceans, attempts answering fundamental questions such as, how did we get here? Are we alone? So the announcements of our discovery spreading all over the world isn't surprising because it taps deep into our imagination and is a small step towards answers, tangible answers to those questions. So if you think about it, actually, it's more than a small step. It seemed to be a reminder of how close we are getting to an answer to this question, simply because we are on the verge on stumbling upon life elsewhere, be it under the surface of Mars, under the ice crust of Enceladus or Europa, around planets such as TRAPPIST-1, or maybe even in the clouds of Venus. We are about to stumble upon life elsewhere simply because it is inevitable. Inevitable just as the pace at which we are growing aware of our surrounding matches the pace at which we are developing new technology. And I believe that 2017, the year we found TRAPPIST-1, is an excellent example for this. On that year, we found the TRAPPIST-1 planet, but a few months after, humanity discovered the first object coming from the outside of the solar system, just passing through, and discovered the first signs of gravitational waves. And these were predicted 100 years ago, right? So to me, the fact that these 3 eras of astronomy opened just within a few months from each other really reflects the extent to which we are increasingly awakening to the universe. So ultimately, the question for me isn't if or when we are going to find life elsewhere, but rather we are going to find life elsewhere. What are we going to do about it, right? Because it is an important experience for our species, a profound one because it will transform our worldview. And as it transforms our worldview, it will help transform us. If a third of the world population can be captivated by the revived prospect of finding life elsewhere, think about the power for change that is rooted in the announcement of its actual discovery. When Copernicus claimed that Earth was not the center of the universe, it triggered a revolution through which religion, science, and society had to adapt to this new worldview. For this reason, when I give this kind of talk to social, industrial, political leaders, I meet them after a few minutes with the same question I just asked you. What are we going to do about this? But in the demanding times we're facing right now, it seems like it would be such a waste to not think about how we could leverage the potential of this once-in-history experience. And so with that in mind, I started this class here at MIT. I'm not going to go into the details, but that's really what we want to think about. What is the scope, the prospect for such a transformative experience? I'm not going to go further down this rabbit hole because it's not exactly the point of the talk, but this is a context within which we work. The science we do has profound transformative potential. And now that this is said, I'll let you ponder all of this and take you on our very own space odyssey for the rest of the day, which start with the sirens, those worlds not so far away, exoplanets. Why do we care about exoplanets? Well, the fact is, there's a lot we can learn in our own solar system, which has planets of its own, but it really is only one sample. And so everything we've learned for over a century now is limited. In the same way as if you were to survey people from a different family, different humans, but that still have a history, probably shared values. So there's only so much you can learn about humans, survey that one family. So when we moved to other worlds, we found things that were unexpected. We found planets free-floating in the galaxy without stars. Planet with multiple stars, like Kepler-16b, that offer these iconic double sunset like Tatooine in Star Wars. We found planet with multiple rings, like this one, 37 rings, about a few hundred times the extent of Saturn rings. So big that if Saturn had such rings, it would be bigger and brighter than the moon in the sky. We've even found planets dying around their stars, being grinded apart, pulled apart by the gravitational field of their star. That's how much diversity we've found, and it has forced us to revisit our understanding of planet formation and evolution. Now you may ask, okay, how do you detect and study those worlds? Well, I'm sure you've noticed we've used a lot of artistic rendering, posters, and there's a reason for that. Exoplanets aren't planets. Well, they are around other stars, but we study them in a very different fashion. When I think of planets, I think about the spatial feature of Saturn, its ring, the zone and band of Jupiter. For exoplanets, things are slightly different. This is an exoplanetary system right at the center, and you can take the biggest telescope you have. That's all you get. One bright dot, the light from the star, and anything that could be around it, planets, for example, concentrated on a few pixels on the detector. Now you understand the posters. Now, what can we do with this? How can we study a whole planetary system from one bright dot? Well, we can use data science. I'm going to introduce you to the basics here. That flux, or that bright dot has a flux that change over time, as well as color. So we can use that time and color or wavelength dependence to extract information about the different component of the system. Let's move to the first two detection techniques that have been used. The first one is called the radial velocity because the star may be wobbling towards you and away from you if it has a companion. And through what we call the Doppler effect, which is the same effect as what raises the pitch of an ambulance when it comes towards you and then decrease it when it goes away from you, the stellar spectrum is going to get to higher energy level going towards you to the blue, and then lower energy level going to away from you to the red. The periodicity of that modulation will give you the orbital period of the companion, and then how much the star actually moves will tell you about the mass of the companion. The other technique that's more intuitive is the transit technique. When something passes in front of the star, it's going to be masking the star, and a flux drop will be associated to the planet-to-star area ratio, so we can get the size of the planet itself. The first exoplanet were observed with the radial velocity technique in the 1995 and onwards. Transit started in 1999 and onwards. Soon enough, in the early 2000s, we got planets for which we could get both. So we could talk about density, meaning we could talk about bulk composition. Is it mostly a big ball of iron or a fluffy gas giant? Okay, great. I came in with my PhD thesis to start doing transmission spectroscopy with Professor Sarah Seeger here at MIT. And the idea behind transmission spectroscopy is that when the planet passes in front of its star, there's a tiny bit of the stellar light that's going to go through the atmospheric annulus. And it's going to be imprinted, or is going to encode information about the atmosphere in the spectrum that you get. Okay. Transmission spectroscopy, to think about it more plainly, is exactly what your brain does when you look at someone else's glass and you get to say, that's apple juice, that's orange juice, that's wine, that's water, that's beer. This is what we do. The light go interact with a component in the glass, and based on the color, the wavelength-dependent effect, you get to say, this is what this is. Okay. For exoplanet, it works like this. Here is an exoplanet. The atmosphere on the left is assumed to be opaque, so it masks a star. On the right, it is transparent, so the stellar light can go through. So at lambda 1, at the wavelength or color lambda 1, more of the star is going to be masked, so the transit depth is going to be slightly deeper. On the right, what you'll see is a transmission spectrum of one exoplanet observed by 2013 with the Hubble Space Telescope. And you can see that the transit depth is slightly higher, so it is slightly deeper, when you look at the planet at around 1.4 micron, which allows us to say that there's something in the planetary atmosphere that is blocking the light at the atmospheric level. And that one thing is actually water vapor. Okay? So this is what we could do with the Hubble Space Telescope and this kind of data sets. Things naturally changed when the hero came in, the James Webb Space Telescope, or JWST, simply because it is a machine designed to do exactly this kind of science. It has a much larger aperture, a better spectral resolution, and it covers a wider range of wavelengths or color, so we get to see more molecules. It's a game changer. In terms of information content, we really moved far beyond what we had access to. To showcase that, I'm showing you here the transmission spectrum of an exoplanet with the first detection of CO2. You see here the transit depths increase at around 4.3 micron. This increase in transit depths is due to CO2 in the atmosphere of the planet that allow for more of the star to be masked by the planet. Okay? I'm going to take this spectrum and add it to what we had before for the exact same planets. This is on the left, information gathered from the Hubble Space Telescope. This is a water feature I showed you just before. This is Spitzer Point, we don't have to look at them, but I'm going to plop right there the data from the James Webb Space Telescope. What can you see? First, you can see that the measurements coming from the James Webb Space Telescope are much more precise. These 1 sigma error bar are, or confidence interval if you wish, are much smaller than what we had with the Hubble Space Telescope. So the precision of the data is increased significantly. In addition to that, we have many more data points per wavelength spread. So we get to really sample these molecular features. Obviously, we now have data for the whole wavelength range. So what does it mean in terms of what we can do with this transmission spectra? Well, we can move beyond simple molecular identification. That's really what's important. Instead of just saying, this is orange juice, we get to say, is it with pulp, without pulp? How much dilution do we have there? How much water is with this orange juice? Wait, is this a mimosa? Wait, is this orange juice at room temperature or cold? Basically, we really get to go and talk about the actual temperature, pressure, composition profile of this exoplanet atmosphere, which is what's needed in order to talk about habitability, sense of life, and so forth. So this is what we could be doing with JWST. The challenge we're facing are new, because we have been developing models over the years that were well suited for the data quality that we had with the Hubble Space Telescope. And now that we're moving to a whole other level of information content, the fidelity of our models are not sufficient. They are not close enough to the reality of the universe to translate the observation into reliable inferences. What does that look like? Let's talk about these light-matter interactions, which are key to translating remote sensing data. It's not a new problem. Already in 2004 and 2005, people realized that the extent to which they could constrain the amount of water vapor in Jupiter was limited by our understanding of how hundreds of millions of lines of water would be broadening by background gas, temperature, and pressure profile, which are dissimilar to what we get to see or observe water under here on Earth, amongst others. So we took that in and look at what it means for exoplanetary science. And I'm not going to walk you through many plots tonight, but I'm going to use this one. What you see on the left are 9 confidence intervals for the amount of CO2 derived for an exoplanetary atmosphere under the assumption of light-matter interaction. So each of these color scheme correspond to our understanding of how light interacts with CO2 to lead to the molecular features that we're detecting. Okay? So, a few things to unpack here. The width of this profile is directly informed by the precision of the instrument. The more precise the data, the more narrow these profiles are going to be. Then what you can appreciate is that each of these models, per the precision of JWST, are telling us a different story. Before, these profiles, with, for example, the precision of HST, were much broader. They would probably encompass the whole spread that we see that appears to be discrepancy between opacity models, which means the opacities that we had, or the light matter interaction model that we had, were good enough for the precision of HST data. But now, the instrument is so good that we start to reveal the discrepancies between the story different models tell us from the same data set. In other words, we're facing what we called or coined an opacity-driven accuracy wall, where the scientific insights that we can get are limited and are underperforming what we could be doing with the instrument easily by 10x. Okay? So the good news is that we actually don't necessarily need to go back to laboratory measurements, which can be expensive, time-consuming, resource-consuming, or even at times dangerous, like CO2 in a hydrogen background. But we can leverage new high-performance computer to do the calculation from first principles, which is what ab initio here means. And we did just that. We developed a framework to show that doing so lead to a scalable solution. And I'm introducing you to the solution so that you know that we have things mostly under control, but also to introduce you to some interesting prospect, especially for industry later. The other challenge we have to face relates to stars. We just don't know stars well enough to handle their contribution to the spectrum. And I'm going to go quickly through this just to let you know that when we observe a transmission spectrum, there's actually also information from the star coming from spots, faculae, flares that are coming in. And I'm saying this because you might have seen press releases that look like this, where we can say that we found water vapor, but we actually cannot say if it's from the planet or from the star itself. Yet, for the point of this talk, I want you to know that we have things under control. We've worked on these problems for more than 5 years now in the group and with collaborators, and we found mitigation and actually solution towards some of these problems to such an extent that I can say, going forward, as we have things under control, let's assume that the search for exohabitats is now unlocked. Which leads me to the new plot line we need to make that within the decade. So we're going to go back to TRAPPIST-1 and look at what needs to be done to get to a place of assessing its habitability, liquid water, or inhabitability, life. The first thing we want to do when we find a terrestrial planet is to assess if it still has what we call a primordial atmosphere, an atmosphere that is dominated by hydrogen and helium, the one that planets wrap themselves with as they form. And typically, terrestrial planets lose them, which is a good thing because hydrogen and helium atmosphere have a very strong greenhouse gas effect. So if the temperate TRAPPIST-1 planet had such an atmosphere, they would actually not be temperate at all, and they would be uninhabitable. So I was lucky enough to lead the programs with the Hubble Space Telescope to do that from 2016 to 2018 and exclude that possibility. So we ruled that out, and we turned to the other possibilities, Venus-like atmosphere, Earth-like atmosphere, maybe none, or almost none like Mars, which required the James Webb Space Telescope. The launch got delayed, so in the meantime, we brought 100 or so experts together to draft what would be the plot line to work with, a roadmap to tell us how to go from a new terrestrial planet to this green box where we can say, you know what, we've done the jobs with JWST. The exploration is complete. I'm not going to walk you through each of the steps. I'm only going to attract your attention to a couple of the corners. This one first. This is where we would like to go with one of these planets, a place where we've seen atmospheric signals, so we know there is an atmosphere. We found some intriguing features, and I'm going to talk about that in a second. And then we get to spend even more time on it to assess if these features are coming from life or something else that is completely unexpected, exciting. What you see here is dCO2. It might be cryptic, but this is where the plot twist comes into play. dCO2 refers to carbon depletion, or atmospheric carbon depletion specifically. Why did we need a plot twist? Because the old paradigms were just not working with current technology. For example, we were thinking of identifying water, looking for ocean glint, like a reflection as the planet-orbited star of the sunlight on its oceans, which is what we did for Titan. We can see here the sun glint on Titan's lake. And for life, we were thinking notably to search for oxygen, simply because oxygen clearly showed up on Earth through big oxygenation phase supported by a planetary scale biomass. Oxygen, obviously, actually not so much, because oxygen is challenging due to a couple of things. First, it has many false positives. There are quite a few ways for oxygen to show up in planetary atmosphere without life being there. And it's difficult to say, if the context is conducive to oxygen being a true biosignature or not. And on top of that, oxygen is a boring molecule. It has very, very limited way to interact with light. Two same atom, linear molecule. So the features of oxygen, absorption feature of oxygen, are very, very tiny. They are right there, and you can't see them compared to other absorber. So not the best pathway to assess for the presence of life with current technology. So as our MIT audience, I'm happy to let you know that the idea behind this plot twist came from teaching a class. I've been teaching 12/4/20 and 6/1 for a little while now, and this is a slide that I showed over and over until it struck me that the absence of CO2 in Earth's atmosphere really is key to enabling the next step for exoplanetary science. Why? Because CO2 isn't in Earth owing to strong water cycle that cleaned our atmosphere, and then plate tectonics stored a lot of that carbon in the crust and mantle. Right? So as you now know, that CO2 has a nice absorption feature that can be observed with JWST. You can now appreciate the fact that looking for CO2 in the atmosphere of planets in a system and identify some of the planet as clearly missing CO2 compared to the other one would be a sign of strong water cycle and or a strong biomass that is consuming this carbon to build itself and ejecting CO2 as a waste product. So the new paradigm here, and it's important conceptually, just came from the idea of not looking for what is added in the signal we get, if water is there, a glint, or if life is there, oxygen, signs of oxygen, but rather looking at what is missing when we study this planet, either due, again, to a strong water cycle or life itself. And then, because we do this using CO2, which is easily detectable with JWST, we can do so. What I mean by do so is habitability or inhabitability assessment with current technology. And this is where we're going to take a break. And for this break, and questions, of course, for the first Q&A, I'm going to welcome today's moderator, the top-notch scientist, colleague, and friend, Dr. Bernanoff. I'm going to stop sharing my screen, take the question, and then we get back in a few minutes.
Hello, everyone, and thank you so much, Julien. It was a great first part. It's not every day that we get to hear and see a solid plan for finding habitable worlds. And I know our audience has a lot of questions, so let's dive in. You mentioned the TROPICS-1 system quite a few times. That system has 7 transiting exoplanets, and one of the questions is about the challenges of discriminating signals from multiple planets in one system. Could you elaborate a bit more how difficult it was to find those planets?
This is such a great question. And I think you and I could actually talk to this because Artem was actually in Liège when the first planet in the solar system was discovered. And so he was also part of this discovery. The issue that we were facing at the time is that we were observing the system from the ground. And as you can imagine, when a transit happens, you cannot easily associate that with an orbital period because there's so many hours or days or night that can happen between the first transit and whichever transit you find after. So pairing them was a challenge until we managed to convince NASA to let us use the Spitzer Space Telescope. It's basically Hubble's cousin in the infrared, and we could just stare at the system for 20 days. And by doing so, the continuous monitoring allows us to very easily pair the planets owing to their size, which leads to the transit depths, as well as the periodicity of their transit. So the only way to do that in a reliable manner when you have so many planets was to perform a continuous stare. Great question.
Thank you. Another question is related to intelligent life. So you mentioned you were saying search for life, but what do you mean? Do you mean intelligent life? Intelligent life? Ooh, are you sure it even exists?
It's another great question. Okay. So believe it or not, searching for some form of intelligence might be easier than searching for life. Why? Because as the process of life complexify, the type of chemistry it gets to do move further and further away from geological processes, right? As I said, oxygen is difficult to pinpoint. There's many false positives because it's a chemistry that is not too far from geological processes. There are many ways geology produce oxygen as a gas. However, as life form has complexified here on Earth, we can, for example, think of other gases such as CFCs that are clearly technosignature, right? There is no planet that is going to produce CFCs. However, if life forms get to a level of intelligence where they get to industrial processes, they can produce gases that are complex enough to be very unlikely produced by geological processes. So that's what I mean by at some point we get to a threshold where life have evolved far enough from the traditional geological processes that it can produce gases that are more easily identified as non-geological.
Thank you. And related to this is a question whether MIT performs search for extraterrestrial intelligence.
Wow, that is a great question that I don't know if I can give a thorough answer to. So I'm going to say to some extent, but I'm not going to go into the details in this talk.
All right, thank you. Another interesting question is about the even newer technologies that's what already exists. So James Webb, we have it now, but what about even more distant future? Are there anything that excites you the most?
Okay, yeah. And you feel free to answer those questions too, by the way, just to make sure that we both get to participate. So there are a couple of observatories that are potentially in the market. The HWO, the Habitable World Observatory, is one of the concepts that could be flying as next mission. I do invite you guys to look into that. There is also a new concept that I'm actually excited about. It's called the Nautilus, and that use new technology from an optical point of view. It's pressed molded lenses, so it can lead to a scalable solution. You don't design a one-shot telescope, but you can design 50 of them, 80-meter class telescopes, and send them to space for different science purposes. So I do think, as I was saying before, that there is humanity is on a hockey stick from a technological point of view. So there's a lot that we can't even foresee for the next 10 years. But there's a lot to be excited about.
Yeah, it's maybe worth mentioning here that many discoveries done with the HST telescope were amazing in the exoplanetary science, but keep in mind that Hubble was never designed to do that. And who knows what James Webb will find.
Totally.
The next question, I think it's a perfect bridge for the part 2 and 3. And it's about the technologies which were developed for exoplanet science, but then they unexpectedly benefited planetary defense.
Yeah, totally. So should I answer that, or should we just move into part 2? What do you say?
Maybe answer shortly now.
Okay. Yeah, so I can tell you that you know what? Actually, let's go to the slides. I think it makes more sense because it just brings nicely to part two and how things actually worked out. So I'm gonna share my screen again, and we're gonna take it to part two, which talks about. Let me see if I can. There we go. Which actually talks about Earth decameter neighbors. And what I mean by decameters, it's asteroids that are of sizes of a few tens of meters, potentially up to 100 meters or so. And to talk about that and to build upon the question, because I didn't give an answer, but to give an answer also to the question that was just asked by Artem, for you, I'm going to go back to this roadmap. And this time focus on the top left corner. Why? Because here we get to talk about something different. We get to talk about emission spectroscopy. Instead of using the light from the star going through the planetary atmosphere, this time for emission, we are studying the thermal emission of planets, terrestrial planets. Why does that matter? Because how hot a planet is directly affected by the presence or absence of an atmosphere, because the atmosphere gets to trap the heat from the star and redistribute it. So typically the first step of analysis or study for new terrestrial planets are rooted in performing some form of emission spectroscopy. Now, this is where we get to power asteroid science by doing exoplanetary science. Because when we do that, we observed at wavelength range or color where these planets are bright. And as you may remember, if you've taken classes here at MIT on the topic or after, the wavelengths at which an object or a person is bright depends on their temperature. So if we use the best observation mode on JWST to observe temperate planets, we are observing that wavelength range where everything that's temperate in the universe over the line of sight is the brightest. Temperate is defined by Earth temperature, which itself is defined by how close to the sun it is, which means that when we're observing the temperate world of TRAPPIST-1, we're also sensitive to anything that's temperate or close to temperate in the solar system, including nearby asteroids, and that's how everything connects. The capability of JWST to perform high-precision mid-infrared observation, where temperate worlds are the brightest, is what also allows us to be partially sensitive to asteroids. And this is how exoplanetary science power asteroid science. You can see this here. You see here the radiation density emission reflection spectrum of synthetic objects at different distance. AU is the astronomical unit. 1 AU is the distance from Earth to the Sun. The first bump that you see here is the reflection of the sun-like emission, the sun spectrum, sorry about that. And then what you see here is the thermal emission of the object itself. And so between, 10 and 30 micron is typically where objects between Earth and Jupiter are the brightest. And this is actually 15 micron, typically where we do the core science for emission spectroscopy of exoplanets. So when we turn to TRAPPIST-1 to study the emission spectrum of its innermost planet, TRAPPIST-1b and c, we got to be super sensitive to asteroids. That just kept on photobombing our observation of TRAPPIST-1 with JWST. You can see here very bright objects that are known that were crossing the field of view. What you cannot see are these 4 objects that are shown here because they were too faint to be seen on single exposures. But there is a technique that uses graphic processing units that are not cheap, so we can use that easily, that looks at any potential velocity vector of unknown asteroid and shift and stack the images to help them shine through the noise. So that's what we implemented. And so the improvement in our capability to detect asteroid is really rooted into that. It's rooted in the fact that we had the enhanced detection capability of JWST in the mid-infrared combined with new data processing techniques using GPU technology. Okay. And so with that, we got to reveal objects much smaller than ever before, right? Our capabilities were typically capped for objects in the main belt. The main belt is a reservoir of asteroids between Mars and Jupiter. Our capability for these objects were typically of, kilometer-sized objects. These are in green known asteroids. And with what we did with Artem, we got to go all the way down to 10-meter-sized object and find way more than ever before at larger sizes. To give you a sense of that, what I show on the right is a size-frequency distribution. This is the size-frequency distribution of the main belt as we knew it before. It was capped at 1 kilometer in size, and we knew that there were about 2 million of main belt objects with size of 1 kilometer and above. We brought this in on the table. We brought this size-frequency distribution all the way down to 10-meter size objects and allowed us to say that there is about 10 billion 10-meter and above asteroid in the main belt. We also got to reveal this little kink here at about 100 meters that shows the transition into what we call a collisional regime. There are way more small objects as you go to smaller and smaller size. And that's due to the fact that any object below 100 meters is easily grinded down by a bunch of collisions. Grinded down, but also easily moved onto different orbits. So we're basically probing a transition from the main belt to the near-Earth object population. So that's where the magic happens to form potential meteorites. In terms of detection capability, you can view it this way. This is what we could do with PREVENT technology from Earth. We were sensitive to near-Earth objects that are decameters when they pass close to Earth, but not when they are far away. Now we get to detect them and potentially follow them up all the way out to the main belt. Obviously, it's important also for planetary defense. It's not just important for science. I'm going to show this to you with a real case example for 2024 YF4. When Artem and I wrapped up our paper, we decided to make that clear at the end of the paper that what we just showcased, which is of importance for science, was also of importance for planetary defense, because we can now assess the size of object further out through JWST mid-infrared capabilities, as well as constrain or follow them up so we can, with higher precision, predict their orbit for potential impact of the future, in the future. We were lucky. A couple of weeks after we published this, we had asteroid 2024 YR4 show up all over the news. So we could move forward. To put 2024 YR4 into perspective, I'm going to show you a couple of previous decameter encounter. The one that's the closest to home time-wise is Chelyabinsk in 2013 that led to 14 people being injured. And that's about the size of the object. And I thank our alumni, Dr. Heidi Amel, for this, and of course Michael Carroll for this picture. If we go further back in time, the interaction with Earth that is the closest to 2024 YR4, which is not going to impact the Earth. So we prove that now. It's Tunguska in 1908, which led to a 5 megaton explosion 12 kilometers above the surface. To give you a sense of the consequences of that, this is Washington, D.C., and this is the zone or the area that was destroyed. All the trees were put down by the blast happening there. So it can be consequential if it happens in areas that are populated, but it remains a localized effect in the context of Earth. And what I mean by it remain a localized effect, potential impact of decameter objects. So as you can see in Heidi's post, there's JWST data that was spending to provide the size, which led to what we pitched in the Nature paper. So with Andrew Rifkin, who also is an alumni of MIT EAPS and happens to be the PI of the DART mission that was mentioned by Whitney at the beginning, we turned JWST to the targets and assessed its size, 60-meter size, not too far from what happened behind Tunguska. In the meantime, the cone of potential trajectory for 2032, which is when an impact could have been possible with Earth, shrunk as we got more data about the orbit of the asteroid. The cone of probability refined. Earth moved out of it, so no worries, no risk of impact in 2032 with Earth, but it's centered on the moon, and the probability for impact with the moon increased substantially, which led to questions like this. So early on, we got the gist that this could be happening. We also appreciated the fact that current protocol for planetary defense only include handling impactor of Earth. The moon is actually not discussed in these. So I did back of the envelope calculation, brought some students in, and then we realized that 60-meter object crashing on the moon, that's a 1 kilometer crater, and that's a lot of material sent to cislunar space, to the extent that it could be a threat to our fleet of satellites. So again, we turn back to NASA, pitch that. In contrast to a localized effect of a 60-meter impactor, the evolution of the ejected dust in the Earth-Moon system could make such a lunar impact of higher significance to the entire Earth population. Probability is low, but it's good to still move forward. And we move forward as followed. We showcase that with current technology from the ground, we would have to wait until 2028 to do something about it. And we wanted to buy decision maker a couple of years of bonus to make decision. And this couple of years can come from this specific window. Let me unpack that for you. What you see here is, detection level as a function of time. From the ground, the asteroid was only visible down to May 2025 and will be visible again or detectable again in 2028. We showed that with our approach, we can actually get this asteroid to be detected with generosity in March 2026, so we can get a better understanding of its orbit by March 2026. So stay tuned. By that point, we'll be able to assess, what this cone of probability look like. Is it concentrating on the moon, or we get to see the same as we saw for Earth? As the cone narrows, as we get a better constraint on that orbit, we push both Earth and the moon out of the probable traces. So that's it for part 2. Now, because you're an MIT audience, I want to bring you into other opportunities. We talk about search for life, planetary defense. There's lots of cool stuff on top of that that could be happening and that we want to attract your attention to. First and foremost, I want to talk about the power of ab initio calculation, not just for exoplanetary science, but also for science as a whole and for industry. And to unleash its power, we need AI. I highlighted how using first principle calculation or ab initio calculation, we can provide a scalable solution to the opacity challenge in exoplanetary science. But the reality is that anything using remote sensing, specifically using spectroscopy as a diagnostic tool, can benefit from such framework. I'm thinking here about climate modeling, radiative transfer, energy budget, combustion, propulsion, medicine, for example, studying the disease through the breath of patient, manufacturing, quality control, even plasma, all the way down to control for nuclear fusion. All of this can benefit from reliable ab initio calculation. The bottleneck here, though, is that we're moving to such complex sets of equations and code that it's really beyond human capability. So if I reframe this, the bottleneck that we're facing is that modern spectroscopy produces equations beyond human capacity to derive and validate. And the breakthroughs are clear, right, in all of these fields I mentioned. So what we're thinking about now is to train an AI agent, an AI spectroscopic, from first principle, so fully bottom up, so it can generate reliable equations at scale and unlock this breakthrough platform for all of this field, from science to medicine to industry. The other incredible opportunity that we're looking at now is to build a hub for planetary defense and planetary resources at MIT. I mentioned planetary resources a few times, and I didn't really unpack that. So what do I mean by planetary resources? I see space as being the place where we will be powering a new industrial renaissance. I'm sure you've heard of NASA's Psyche mission going to this quadrillion-dollar asteroid. It's actually a 10,000 to 100,000 trillion or quadrillion-dollar asteroid. That's 10 billion of billions of dollars, lots of zeros. And to put it in, to put it in context, it's 2 million times NVIDIA's valuation today. So we're really looking at a pathway to a new economy. We're looking at multi-quadrillion or quintillion-dollar economy with little environmental costs, considering what it means to mine Earth those days. And by doing so, we can unlock a new era of manufacturing, in-space manufacturing. And through this in-space and resource acquisition, so manufacturing and acquisition, we can reliably unlock access to Moon and Mars settlement. So that's what I mean by planetary resource and potential consequences for this. I foresee that hub for planetary defense and resources as a two-bird, one-stone situation. Why? Because the challenges that we face for planetary defense unlock planetary defense, but also planetary resource acquisition. It is rooted in the fact that decay matter asteroids are frequent megaton class impactor, the key word here being frequent, far more frequent than what we've seen before. As you've seen in this size frequency distribution, there are way more small objects. And the issue is that current protocol and mitigation tools are just not ready or scalable solution for this population of impactor. So the opportunity for MIT is, and that's what we're working on right now, to build next-gen detection and characterization network with facilities from the visible, infrared, all the way out to radar. I'll talk about that, as well as developing a multidisciplinary ecosystem. And then we would love to launch, mini-DART, nanosat programs to provide cost-effective, rapid response to such a situation. That's our next step. How would that be a dual payoff? Well, by doing so, we would open the path to turning selected NEOs into resource hubs for in-orbit manufacturing. What that means is that the network that we would develop for detection characterization of potential threats could also be used to identify and characterize the best NEOs for resource acquisition. And importantly, the mitigation capabilities we developed could be tuned such that we could use them to turn the selected NEOs into moons for Earth, hence the in-orbit mining and manufacturing. So let's talk briefly about MIT's legacy with radar, because one of the important facilities we've been working on upgrading is Haystack. Haystack is one of the largest and most sensitive telescopes in the world operating at these frequencies, the frequencies that are required to easily get size and even the topology of asteroids, which is important to select impact sites. And one of the upgrades that we're interested in doing is really to achieve its full potential for asteroid investigation, and again, especially size and topology assessment. And if you're interested in hearing more or even visiting, if you're in the area, please connect with them. They're open for tours, and I guarantee you it's worth it. I was talking about growing an ecosystem. Of course, we're bringing the wide range of expertise that we have in EAPS and on campus together for this. And for the first time, we're even starting to bring this down to an education offering. So if you're interested in hearing about planetary defense, there will be a workshop. This IAP, here are the dates. It's open to all. So if you're interested, please reach out to Saverio at this email address right there. In conclusion, MIT is the leading institution not only to help us find signs of life elsewhere, to help us understand how we got here, if we are alone, and to provide context for climate, habitability, potentially even intelligence, as I said earlier. It's also at the forefront to help us understand where we're going and to define, in fact, where we're going. And so through this talk, I hope you got to enjoy where we're at with regard to finding life elsewhere, defining Earth, but also bringing us and our industry to a whole new level. So I'm going to leave you with my takeaway message, highlight the fact that really humanity is one step away from becoming this multiplanetary species, and with your help, I have no doubt we will get there. I hope you enjoyed the talk, and I look forward to your question. Thank you.
Thank you again.
Yeah.
It was great, super interesting. And thank you to our audience for another round of excellent questions. So, Julien, what are the bottlenecks? You briefly said that protocols and mitigation tools are not ready or scalable. So what's the problem? And how can we overcome this?
Yeah, so is the question related to planetary defense?
Yes.
Yeah, okay. So some of the bottlenecks we have relates to the sheer number of potential impactor we're going to deal with, and the access to capabilities to follow up on them. So that's one of the core problem. Then with regard to mitigation strategy, we've talked about the DART mission as being a success story to showcase that we can affect the trajectory of an object. This was a large-scale asteroid. The potential threat we'll be facing this century will be in the decameter regime. So object that will be 40 to 60, maybe 100 meters in size, maybe the object that we'll be playing with. And so there is room for cost-effective, so cheap, as well as fast response mission that we could look into that would also support planetary resources, as I was highlighting.
So you mentioned decameter asteroids in the main belt. And there are also near-Earth asteroids, which are much closer to Earth. So why do we Why do we need to care about those small objects in the main belt? They are super far away.
What is meant by why do we need to care?
I mean, how do they become near-Earth asteroids? How?
Oh, is that the question? Sorry.
Yeah, just to clarify this, that they.
Yeah, of course. So, we're scientists at the base. I mean, technically, I'm an engineer by training, and then moved into this whole thing. But what we're looking at here is it was a science case, like with for free, we could do bonus science using GWST and our observation of TRAPPIST-1. So we did that together, and by demonstrating that we could observe and detect diameter size all the way out to the main belt, we showcase that when we have potential impactor all the way down to sizes that matter for this type of threat, we could monitor them all the way out to the main belt. So that's a connection point there. Now, these near-Earth objects were before main belt object, and they just through interaction with the rest of the main belt or Jupiter, they evolve into near-Earth objects. So that's the relationship between the two. Most of the near-Earth objects that we're looking at are actually coming from the main belt. That's what I meant earlier by this MBS2 NEO population.
Yeah, thank you. So you mentioned your background is in engineering. The question is, what is it about planetary science that interested you so much that you kind of transitioned?
Yeah, okay. Fun fact. So I came here as an aerospace engineer in 2010 to work with Sarah Seeger on a nanosat mission. And then she introduced me to the prospect of at some point getting to a point where we can study the atmosphere of other world. And as a student coming here, I was like, wow, that sounds cool. Like if you think about, again, the impact on humanity, you can cure disease, you can do a bunch of things from a technological point of view. But shaping humanity's perspective on itself and on Earth, or have an impact on that, not shaping it, I'm not going to. It's incredible. So that prospect got me interested into exoplanetary science. And then, TRAPPIST-1 happened for the two of us. I had the chance to open the era of terrestrial planet atmospheric study with Hubble. And here we are. So that's what happened.
Thanks for sharing your journey. Again, speaking about TRAPPIST-1. So the TRAPPIST-1 planets are tidally locked, and they are super close to their host star. So can there be life given these conditions?
Love it. So let's unpack what tidally locked mean, right?
Please, yes.
So tidally locked mean that the rotation period of the object is the same as its orbital period. That's basically what happened for the moon. The moon turned upon itself in the same time it turns around the Earth, which means that the moon is always showing the same face to Earth. I'm sure you've noticed that over time. For planets that are close to their star, same thing happens. So they have a permanent day side and a permanent night side, right? Which means there's a strong temperature difference. So if life were to emerge there, we don't know what it would look like. So we move into beliefs. If these planets were to still have a strong solvent, say water is a great solvent for the chemistry that we like to emerge. I believe that life is just the continuity to chemistry and physics. So basically the universe has attractive and repulsive forces. There are processes of different level of complexity that emerge. At some point, humanity says that's complex enough to be called chemistry, or local enough to be called chemistry, and then that's complex and local enough to be called biology, and then that's complex and local enough to be called intelligence. For me, it's just a continuum of complex processes. And so if that is meant to happen per the fundamental laws of the universe, attraction, retraction, repulsion, I don't see a reason why, if there's the right solvent to allow for chemistry, concentrated enough and complex enough processes to emerge on these planets, for life not to emerge at some point. So that will be the answer.
All right. Well, we'll see what James Webb and other future observatories will tell us.
Sounds great.
We have time for one more question, and it's about the James Webb Space Telescope. So how often do you observe any strange anomalous signals in the data that doesn't fit into current models? And are there any frameworks for systematically looking for unique signals?
That's a great question. I don't know if there are systematic framework to look for such detection, because usually we're very, there's a time crunch. Like you get data to do some transformative science, and you really have to focus on that. The example that we gave, that you and I, Artem, took care of with these asteroids, was fully self-funded. Right? We decided to mine this data set because we knew there would be asteroids. There was a pipeline that you led. And so we didn't have to start from scratch. We had already developed a framework to find asteroids. So it is not easy in today's world to do things for which you've not requested the observation for. So I hope that answers the question. It's relatively easy to do from a data science point of view, but then you do need the resources to make it happen. So I'm not aware of that. We've done some of this by revealing these asteroids, but there's, I'm sure, a lot more to be done. For example, studying flaring activity of stars and this kind of thing. So the archive is there, so anyone who is interested can get access to the data. It's made public by NASA.
Yeah. And I would just add that the first level of looking into spurious signals is just visualizing your data, your images, and looking by eye. Not often it is done. People often go straight to analyzing the plots, writing equations, but sometimes it's just to see the beauty of the data you have, like a color image, something like that. All right. Unfortunately, that's all the time we have today. And thank you again for taking us on a journey from distant exoplanets to our backyard filled with asteroids. And that's a good reminder that science helps us look outward while also safeguarding our home. Of course, a big thank you to the MIT Alumni Association for organizing this program and bringing us together for such a timely and important discussion. And thank you for having me today, and to all of you for very thoughtful questions. Thank you again, and goodbye.